So my name is Meister, and I will present our new ray tracing framework, HIPRT, which is a ray tracing framework tailored for AMD GPUs, and we are focusing on professional rendering. So we have advanced rendering features such as multi-level instancing, motion blur, intersection filters, and others. As a core acceleration data structure, we use bounding volume hierarchy, BVH, which provides scalable construction. And as a minor contribution, we also proposed a new BVH construction algorithm using spatial splits on GPU. HIPRT is cross-platform thanks to HIP, which is a kernel language syntactically almost identical to CUDA, but it can be compiled also for AMD GPUs. It runs on both Windows and Linux systems, and HIPRT can run also on GPUs without hardware acceleration compared, for example, to Vulkan or DirectX, which might be useful, for example, on MI GPUs, which might be useful for scientific computing, for example. The code base is relatively small, less than 20,000 lines of code, and this is thanks to HIP, and HIP supports modern C++ standards, so we can use all these nice modern features such as templates, lambdas, and other constructs. And last but not least, it's open source. HIPRT was already integrated into several renderers, so the most famous one, Blender Cycles. Next, we have PBRT4, version 4, which supports also GPU ray tracing, so we implemented another backend in HIPRT, very popular research-oriented or educative framework. And the last is our Radeon Pro Render. So we are not limited by standards given by third parties like DirectX or Vulkan, so we can design our own API, so we can focus really to make it very easy to use. This is very sensitive topic, I would say, but we believe that ray tracing pipeline is not very, programmable pipeline is not very suitable for professional rendering. In general, it is opaque and difficult to debug. Shader binding table is a very difficult concept to grasp. There are whole chapters explaining how to set it up. And for professional rendering, it's not suitable because it couples ray tracing and shading. And shading is typically way more complex in professional renderers. So yeah, it's great concept for real-time ray tracing, like games. So it's like natural transition from rasterization pipeline, but not that good for professional rendering. It's a kind of artificial construct. So HIPRT follows similar philosophy as Embry, so we want to have a minimal host code setup, unlike Vulkan, for example. We are providing just ray tracing functionality. All other computations are on the application side. So, for example, shading and also data assignment, which is in other APIs done through shader binding table. We really cannot avoid custom functions. We need intersection functions for custom primitives, and the second type we have is intersection filters that I will explain later. But in our case, it's just 2D table. One dimension is ray type, and the other dimension is geometry type. Here you can see minimal example of HIPRT API. On the left side, we have the host code set up, or just part of that, where we create triangle mesh defined by indices and vertices. Then we create HIPRT geometry, which is BLES in HIPRT. We build it. So in this example, we have just one level hierarchy, and the last line is a kernel compilation, trace kernel compilation. In this case, we use runtime API, but it can be done also offline. On the right side is the corresponding trace kernel, which is nothing else than standard HIP kernel with injected HIPRT functionality. So we first create array. This is on the application side. Then we create HIPRT traversal object passing the geometry and the array, and then we find the intersection. And again, how the result is used is on the application side. So as I mentioned, as a core acceleration data structure, we use BVH. We have 3 options, quality options, like fast build, balanced build, and on the next slide, high quality build. Fast build is implemented as LBVH, very fast construction algorithm based on sorting geometric primitives along the Morton curve. And after the sorting, we can easily extract this implicit BVH given by this sorting in a single kernel launch. But the quality is not that good because we don't optimize the surface areas of internal nodes at all, not explicitly at least. So that's why we have a balanced build, which is still relatively fast, but yet the quality is much better. It is a bottom-up iterative, our implementation is based on block algorithm, parallel ordered clustering. It is a bottom-up approach, building BVH iteratively, where in each iteration we merge multiple cluster pairs. Our current implementation is based on block++, which is optimized version of the original algorithm using a single kernel launch per iteration. And yesterday you might saw HBlock, which is like the next evolution of this algorithm. So we plan to replace our current implementation by HBlock very soon. And in this algorithm, we use also like Morton curve, but to find the nearest neighbors for the clustering. So in this case, we really optimize the surface areas of internal nodes. So the quality is much better. The last option, high quality build, as you can guess, it's if you really aim at highest possible quality at the cost of higher construction times and also like higher memory consumption. Our algorithm is based on the SBVH algorithm originally proposed by Stich and colleagues. Originally it was just a single-threaded CPU algorithm, and we try to reformulate it for GPUs. The motivation is that the standard BVH doesn't cope well with long diagonal triangles. So what we can do is to use spatial splits, which is a technique known from KD trees. So we can achieve tighter bounding boxes, but the cost is that now triangles are referenced in both subtrees. So SBVH is like a top-down approach where we try both standard splits and spatial splits, and we select the one minimizing the SAH cost approximation, which takes into account not just the surface areas, but also the number of references in each subtree. And yeah, our goal was like preserve to quality of the original algorithm, what we achieved, but yeah, the construction times are way higher than like the fast and balanced options. The last option is not a builder, but it's like API custom BVH import that allows user to import his or her own BVH to HIPRT and then use the traversal code, which is I think useful for example, research. Now I would like to talk a bit about features we have in HIPRT. The first one, multi-level instancing, which is generalization of two-level hierarchy into more than 2 levels. We support basically arbitrary number of levels. We need like additional logic, like so we need like a short additional stack to store the hierarchies above, to be able to go from hierarchy, bottom level hierarchy to hierarchy above. And also we need to get the array in that corresponding space. And advantage of this feature is that it can like reduce memory consumption significantly. So, for example, we can render one island on a single GPU in core, which is very like it's a huge scene with 156 million unique primitives and 31 billion instantiated primitives, and this is from the PBRT port. The second feature we have is instance-based motion blur. It is multi-segment motion blur with non-uniform intervals. Multi-segment means that we have multiple keyframes for each instance, and non-uniform intervals means that we can specify the time for each keyframe. So, for example, we might have 3 keyframes with times 0, 0.1, and 1. So, like, you can achieve similar result in optics, but optics supports only uniform intervals, so you need to manually resample into 11 keyframes. The second thing is that we support like correct interpolation even when we use matrices, because we internally decompose matrices into individual components and then we interpolate them separately to get, especially the rotation is the most problematic. To get the correct result, you need to do spherical quaternion-based interpolation. If you interpolate just matrices, if there is no rotation, it's I think okay. But if it includes rotation, you might get like incorrect result, and also like even like singular matrix. Ray traversal use stack-based algorithms, so nothing special. One unique feature we have is that we can specify the traversal stack as a template argument in the traversal object. So we have like 3 predefined stacks from very simple ones, which are easy to set up, to more complex one like this global stack, which provides better performance, but it's slightly more complicated to set it up. You need to manually pass the buffers. And this stack combines shared memory for topmost entries and as a backup global memory for bottommost entries. Yeah, intersection filters that I mentioned before is a second type of custom functions we have in HIPRT. And this is an optional custom callback that allows user to filter out some of the intersection, which is useful, for example, for alpha masking or filtering out of intersections. In programmable pipeline, you can achieve the same result, but you need to use any hit shader even when you want to find like the closest hit, which is like a bit unintuitive, at least for me. Yeah, so far I talked about features and API. Now let me also show you some numbers. So performance comparison. For that purpose, we implemented waveform path tracer, which is nice because we can like separate ray tracing and other computations, so shading. So we can switch different ray tracing implementation while keeping shading the same. We have 2 settings for the scene partitioning, so original 2-level partitioning, which is the more practical case, and the second setting is like pre-transforming everything into a single large instance, which is useful for evaluation because we have one a single SAH cost and a single build time. And we have 2 ray tracing backends. One is HIPRT with our 3 options, and also to demonstrate that a custom BVH import feature, we built the BVH on using Embry on CPU with high quality setting and spatial splits, and then we import it through this API to HIPRT, which is like, besides demonstrating this feature, it is also very good reference method. And for second backend is Vulkan. There are only 2 options, fast build and fast trace. And all tests were executed on AMD Radeon Pro W7900. Here you can see our test scenes. So they are like quite complex, both in geometry and also light transport. So you can see various global illumination phenomena, such as glossy reflections, indirect shadows, and others. So here you can see average, average relative trace times. So like to average over all scenes. So first we need to normalize them to get meaningful numbers. For that purpose we use the block, the green one. So it is always 1. One observation is that the Vulkan is faster for primary rays, but way slower for shadow rays and slower for secondary rays. So HIPRT is faster for shadow rays and secondary rays, and it is also faster. Our SBVH is also, what is interesting, is faster than that imported Embry built BVH, so that's also interesting observation here. So SBVH is pretty good, but there are the build times are way higher, like more than five times higher than for other builders. But this is not like a big problem, as you will see on the next slide. If we reuse the BVH many times, which is the case in the professional rendering, this becomes marginal. So here you can see build time and average build time, again normalized by block and SAH cost. So LBVH is the fastest algorithm overall, followed by block, which is interestingly faster than both Vulkan options. And SBVH is slow, but it provides like the lowest SAH cost, practically the same as Embry imported, like BVH built by Embry imported to HIPRT. This is time to image, which is build time plus trace time for one particular scene. For other scenes, it looks similar. On x-axis, you can see samples per pixel, and at 0, it is offset by build time, so like initial overhead, which is higher for SBVH, but SBVH has higher quality, right? So the per sample overhead is lower, so with increasing number of samples, at certain point it becomes faster than other methods, and in this particular case it is like 64 samples per pixel, which is still pretty good for professional rendering because we use much more samples, right? So to conclude my talk, HIPRT is a new open source ray tracing framework tailored for AMD GPUs. Performance is comparable with Vulkan, maybe slightly higher. I think API is definitely more user-friendly than Vulkan. SBVH provides very good acceleration, ray tracing performance, but the construction is slow. So that's also like one of the points for future work, like to improve the construction speed. It is tailored for professional rendering, so we have these features like motion blur, multi-level instancing, and others. We also pointed out some of the drawbacks of existing APIs, but this is rather minor. For future work, we would like to integrate HBlock, which was presented yesterday. It would be also interesting to introduce new primitive type curve, so optimized primitive for hair or fur, and also our current implementation is hopefully correct, but there is definitely room for optimization, especially of these advanced features like multi-level instancing. So that's all. If you are interested in HIPRT, you can use this QR code or these links. Thank you for your attention, and I'll be happy to answer any questions.
Questions for Daniel?
Yes, I can yell. So you use for a query
think shared execution in ordering would be useful. And how would you do it if you do array query?
Can you repeat the question?
Oh yeah, question is that shader reordering would be useful, and how to do it if we use array query. Yeah, that's a good question. Basically shading is on the application side, so you can like use it after the array. So shading is invoked after you find the intersection, right?
It's okay if you don't have an answer.
Like, yeah, I don't know right now. I don't know right now. Sorry.
So you have mentioned Blender. Is it already part of Blender, or how can I get my hands on it?
The question is whether the Blender is Blender integration is part. Yeah, it's already part of the Blender. I'm not sure like whether the stable release, but at least yeah, it's in the official repository.
In your slide said that your SBVH implementation was GPU-based, top-down, and did spatial splits. Is your top-down approach, is it like one kernel launch with a span of all the triangles in the scene, and that does one level of partitioning, and then another kernel launch for the next level partitions and so on?
Oh yeah, so the question is about SBVH implementation. Yeah, it's very like, I would say naive, yeah, so it's like one kernel, it's like several kernel launches per one iteration.
Okay.
Actually, like, yeah, compared to standard top-down build, it's like, yeah, there are a lot of like caveats with spatial splitting.
So one thing I think that would imply, versus the single-threaded CPU-side SBVH from 2008, is that you spend your spatial split budget on the root nodes and near the top of the tree, which is more efficient than the original SBVH paper, right? If you have this much additional memory allocated for your spatial splits, and you do the splits at the root node, you're decreasing the size of massive AADBs, right? And then you gradually fill up that space, and then when it's gone, that's well before you've reached your leaf nodes. Whereas in the single-threaded SBVH, you're burning that budget down at all levels of the tree. Have you noticed that, and any speed up from that?
Yeah, this is a good question. I think in the original like algorithm CPU version, you don't have like a strict budget, so like you can allocate memory as you want, right? But yeah, in our implementation, it's like that you use like 1.5 of the inputs of the number of triangles, for example, and you allocate and you use it, yeah, until it's like full. So yeah, but I think it depends on in the original algorithm. It depends like what you use for if you use stack or queue, right? If you use queue, it would be similar, I think.
Yeah, in the paper they use this stack, right?
Okay.
So it was a depth first traversal.
Oh, okay.
Okay, so it sounds like.
But I think there is no like strict budget in the original algorithm. It's like that you like stop. You stop when I think the like intersection of both like of the children is like less than some predefined threshold. Yes.
Thanks.
Any last questions for Daniel? Okay, let's thank the speaker again.